Okay, so now we are going to write the code with together, and so I opened one script file, MATLAB regular script file, and I named it as Advection-Diffusion. Okay, and so in this side I'm going to open the slides also. So that is the code, right? So I'm going to let me zoom it up. In the first module I will write how to initialize all the parameters. So I'm going to do, so remember that we are coding for this type of grid point, so that's our grid. So we got 71 in this direction and 41 in this direction and 41 in the membrane also. So let's start writing. First we'll clear all the variables. To clear all, clear screen. Okay, so Lx, what is Lx means? The length in the horizontal direction of the channel. So I'm giving it as, so in meters, okay, 0.3 meters. Okay, so what is Lx means? If you go to the model, so in the channel length in the x direction is Lx. Okay, and Ly is equal to 0.002. So what is Ly is the channel height, so the length in this direction, and that is for the channel. Okay, and so nt means number of seconds. Okay, so I'm giving so actually we are not using nt, just it's already commented. So nx means number of grid points in x direction, we are clear about that, and d is the molecular diffusivity of the species when it is diffusing in the fluids in the channel. Okay, so we already get that value, it's about 1.48 into 10 to the power minus 5, and dt is the turbulent diffusivity. Actually I didn't mention about the turbulent parts in the governing differential equations, because actually the flow is not entirely turbulent. But however, for great accuracy there is a still possibility that there's a small turbulence can be occur, even though we are considering the laminar velocity profile. Okay, so for the sake we are also writing turbulent terms also in our code. Okay, because basically there's nothing special about turbulent diffusivity also. It is just introducing another type of diffusion coefficients. There's nothing associated with the advection terms. Okay, so it is only introducing another type of diffusion coefficient called turbulent diffusivity, and it is just introducing another type of diffusion term. You will see it when we go to the coding. So that's value is 2 e to the power minus 5, and that's turbulent diffusivity, and dx is equal to Lx divided by nx. That is clear, right? So that is the width of the length between two successive grid points in x direction. Okay, so now, so I'm going to define an array. I'll tell you what this array is. Space starting from 0, Lx, nx. Okay, that means you have an array with a length of from they have grid points of nx grid points as 71, and that means there are values of Lx. Okay, Lx means the length of the x direction. Okay, and that 0 to Lx is divided by nx. So in that array, So Lx divided by Nx value will be stored in each and every cell. Okay, clear? So that is we are using it for plotting purposes when you are going to plot the variation of concentrations with respect to x direction and y direction. So that is important in this case, but it's not important in the simulations. Okay, so now we are going to define a number of grid points in y direction. It is 41. Okay, and the discretized length of y direction is Ly divided by Ny. Okay, and again we are doing the same thing for the y direction also. We are going lane space 0, Ly, Ny. Okay, and so Umax is 0.2 means it is the maximum velocity. Okay, the maximum velocity in the channel. That means the maximum velocity will be seen in the center of the channel. Okay, so that is 0.2. so that will be important in our when we are going to get velocity distribution using the Poisson flow. Okay, so now this is a very crucial step, that is defining the time step size. So there's a way to get the time step size. I'll encourage you to go and study CFD methods by Mallasekara. That is a very known handbook of computational fluid dynamics. So in this book it is clearly shown that how you can get the accurate time step to converge the solution. Okay, so otherwise maybe you can get a random time step. Okay, so the time step has to be in the order of magnitude of the geometry that you have, or the discretized cell size. The time step has to be in that range. Okay, so this is a way of getting that. So otherwise if you are getting a very large time step compared to the geometry of the cell, okay, the discretized cell, so that's not going to be a good results, because it's actually avoiding some of the length scales that are very important. So the solution will diverge. Okay, and it is small, the converge will happen. Okay, so solution will not converge in that case also, because it will take a lot of time, and it is take a lot of computational power if you get a very small time step. So we have to get a convenience time step. Okay, so this is the way of getting a convenient time step. So please refer this book, so you will see how this step is derived. It's 0.7 into dy square, okay, by d. And see, it is also already dependent on the diffusion coefficient also. See, so that means actually it says that the diffusion coefficient is a very small part in here. That means that's a very small value. So that means it is basically diffusion means the diffusion time based. You know, it is some, let's say the molecule with diffusion, how much time it will take to travel a unit distance. Okay, based on that concept this relation is derived. Okay, so please refer to that book for more information. Okay, so now I'm going to display dt for, so you see what is the size of this time step for current read. So let's run this code for now. See, so the time step is about 5.6 into 10 to the power minus 5. So it's a very small time step. Okay, so that means if you want to run the simulation for about 5 seconds, so based on your computational power you can imagine how much time it will take to run the simulation. Okay, so because it is taking this time, because actually we are using the explicit finite differencing scheme. So explicit finite differencing scheme is entirely based on the time step size. Okay, so usually, you know, if you go to ANSYS or console or whatever the CFD platform you have, so they are entirely using the implicit scheme. So implicit scheme, there's a time step size doesn't matter. Okay, it will, the solution will converge anyway. Okay, so therefore, but however in our case we are using the explicit scheme. So So in this case we are actually limited by our time step size. Okay, so now the next thing is I'm defining the concentration matrices for each domains, inlet channel domain, membrane and outlet channel domain. Okay, zeros. So I'm initially defining a two-dimensional matrix, ny gamma nx. Okay, so that means there's a matrix that has ny number of rows, nx number of columns. Now I think we are all clear about this. Okay, so ny means we discretized ny in the y direction, but however in MATLAB this y direction is represented by the rows. Okay, and x direction is represented by columns. Okay, so that's why it's ny columns and nx ny rows and nx columns. Cool. Okay, so now cn means zeros, again ny comma nx. Okay, that means C is the concentration at the current time step. Okay, that means and Cn is the concentration at the previous time step. Okay, so we are saving the value of the concentration of the previous time step in Cn and the value of concentration that we are currently calculating in the C matrix. Okay, so because in the explicit scheme the current concentration is calculated by the concentration of previous time step. Okay, so that's why we need two matrices for concentration for this solution. Okay, right. And so CF value actually doesn't go on at the moment. So so now I'm defining another matrix called advection is equal to zeros, again ny nx. That means we know the advective part of our equation, right? That means u del c by del x, right? Advection in x direction. Okay, so that value of that term u del u by del x we are storing in this advection matrix. Okay, so I think that is clear. And diffusion in the same way, we are defining a diffusion matrix with zeros, again the same size. So whatever the value of the diffusion terms in the advection-diffusion equation, that means in here, yeah, so whatever the value of this term, whatever when we compute it for the nth time step, so that will be stored in this matrix, and whatever the value of this term, it will be stored in this matrix, right? Okay, so that is diffusion. Okay, and I'm defining another term, diffusion x is equal to zeros ny comma nx, and diffusion y is equal to zeros ny comma nx. So actually there's no need of writing this diffusion x term actually, because we wrote it as it is the code for a different purpose. So in the current case we don't need actually this term, so I'm going to comment it, because we are not considering the diffusion in x direction, right? We are considering diffusion only in y direction, but only the membrane we consider diffusion in both directions. Okay, and so as we discussed before, we are introducing the turbulent diffusion term. So whatever the value that is calculated by the diffusion term, whatever the value of the diffusion term or the advection-diffusion equation will be stored in this ny in this turbulent diffusion matrix. Okay, and the transport is basically, I'll tell you what it is the addition between advection, diffusion and turbulent diffusion. That is it is the addition of these three matrices. That means if you go here, so in this case add this one, and it will give, and with the turbulent diffusion part also it will look like same like this one, so it will give the transport matrix. Okay, those values will be saved in transport matrix. Okay, zeros in my command. You see that now all, so it is all, everything is based on our grid size, right? Everything, all the matrices is now based on our grid size, right? Because each grid point is value is represented by the cell of a matrix. Okay, now so CAP, so that is d by dy square into dt. Okay, VAP, I will explain these values when you go with the subsequent coding, so it will not make sense to define these values at this point. And display cap CAP. Okay, so let's run this and it will get saved. Okay, now the step is okay, now in this section we will go we'll see how we get the velocity profiles. So I'm going to type this part in the code, and let's try this first. Velocity. So this is the function that actually I wrote to get the velocity profile in the vertical direction. So this function will give the lamina, that parabolic velocity profile in the channel, and UR means the U means velocity profile in the inlet channel, and UR means velocity profile in the outlet channel. I'll show you this function at the last. So it is very simple. So that means for this function I am giving the values ny and nx. So ny will give the height of the channel for each, and for how many numbers, how much time we have to calculate based on the height of the channel, the velocity will be how much, like that. So ly and lx means the parameters, the length and the height of the channel. For it is same for the inlet and exit channel also. So now we are going to write the membrane properties. So the membrane thickness is 0.0009 millimeters micrometers, and nmy is 41, number of grid points in the vertical direction of the membrane, and the effective diffusivity of the membrane is 1.1 to e to the power minus 6 meters square per second. And again we are getting that Lin space vector, so it will be easy for us to plot at the last. Lx and x in x direction, y is equal to space. Okay, and so now we are going to initialize the membrane concentration matrix as we discussed before. So Cm means concentration in the membrane, so it's here. So Cmij. Okay, so we are going to initialize this matrix. Cm is zeros, nmy, comma Next, I think that's clear. And Cmn means the velocity at the previous, the concentration at the previous time step. Zeros. Nm by nx. And diffusion is equal to diffusion for part of the governing diffusion equation, and diffusion in x direction x we are taken as xm. So whatever the term, diffusion term, d effective into del square c by del x square, the value of that term will be stored in this matrix. Zeros and again n by x. Again diffusion in y. Zeros and x. Okay, and so because we need the surface concentration, right, of the membrane. So for that case, so we're going to initialize another matrix called the surface concentration. So I'll tell you what is the use of this when we are using this matrix. So let's initialize matrix with this size in y, nx. So now let's define the matrices for the outlet channel. So Cr is velocity concentrations the previous time step for the outlet channel, nx. Cr means the current time step, and Crn is the previous time step. Zeros ny, nx. Okay, and so the in that equation, advection part is advection of return. So I'm going to option R is equal to 0. What is the advection term in that governing equation? Advection-diffusion equation is this one. And in that governing equation, diffusion part is in diffusion in y direction, diffusion by R is equal to zeros n y, nx. Diffusion in so I'm not going to write diffusion in XR, but I'm going to write diffusion. Okay, so we are not going to use the diffusion in x direction. XR zeros n y, nx. Okay. So we almost defined all the matrices and initialized everything. Okay. Now in this section we're going to write another few parameters, and we're going to initialize how to plot the dynamic contour plot. And so first this is totally MATLAB based, so you please go ahead and study about what is this curve and animated line functions. Animated line, these are actually classes, objects. So I write it like this. So you need this function to get that live plot of concentration variation with time. So as I showed before, so please go ahead and type it, and there are a lot of information available about this object in MATLAB library. And so this label means whatever the I'll put x in this plot. I'm gonna put x time mass in x direction, and in y direction concentration will be there. So I'm going to not take much time typing everything. Okay, so I'll just copy and paste it here. And so the now is very important. So Ka and Kd values are the adsorption and desorption coefficients. So in my in here I just mentioned them as SA and SD, but in the code SA is equal to Ka and SD is equal to Kd. Okay. So the value of Ka and Kd, we took it from experimentally. So it is 0.0056. Okay. And Kd is equal to 0.0069. Okay. So now initial time t is equal to 0, and the maximum working time t is equal to 0.0 seconds. So we already seen that how much our time step is, how small it is. So we gonna write for a very small time and see how it is evolving. CR is a 0.2. What is this? Actually, CR means I'm initialize the concentration of the outlet channel by a initial value of the pollutant or the species that we are going to transport, because the model, if we give 0 in there, so it will create some of the problems, creating imaginary values because of the zeros available in the some of the parts of the matrices. Okay. To avoid that problem, so we are giving an initial value of that pollutant for the outlet channel of the matrix. Okay. So that means 0.29 means the ambient concentration of that pollutant without any source or sink term. Okay. So let's say, for example, we are talking about ozone. So we are supplying ozone to the inlet of the inlet of the inlet channel. Okay. So let's go here. I'll explain this part. So that means basically this is our arrangement, right? So basically when it is in atmosphere, so let's say we are going to supply ozone here, but even though without we are going to supply ozone, so there is some ambient ozone concentration is there. Okay, so that is this concentration 0.29 micrograms per cubic meter. Okay, so we are giving 0.29 for all the matrices, assuming that not in the membrane, but all the inlet and exit channels, assuming it is already present in that concentration. And after that is the initial value of these materials. Okay, and after that we are giving the source term in here. So that value will be changed by addition of new more concentration of the species. Okay. All right. So so I'm going to initialize this. That is a stop 7.48. So that will be the source concentration of the inlet of the inlet channel, and the bottom. I'll explain this what these terms means when you are using it in the code. Figure. So figure is to plot that initially whatever we define from curve, this animated line, so that will be plotted in this figure. Okay. So now so we are going to come to the code. So as it is already, so we got to run. We just run the code inside the time loop. Okay. So what I'm going to write is, I'm first writing the time increment loop. So it's going to be while t less than t. Okay, this t less than t. So I'm going to write n. So this is the main loop. Whatever we write is inside this loop, and so we are going to t is equal to t plus 1. So after each time loop, so time should be incremented, right? So there will be adding so actually it should be t plus dt for each time loop. Okay, right. So now let's give the boundary conditions. So now we write C in is equal to 7.48 micrograms per cubic meter. So C in means what? The concentration, or we are supplying concentration at the inlet of the inlet channel. Okay, it is here. Okay, it is here, in here. Okay, in this area, inlet concentration. So we are going to all these grid points. So we are going to give C in is equal to 7.48. So put it down a little bit here. Okay. Okay. To represent that, so this we are going to give C all rows, comma first column of the C matrix is going to equal to C in, right? Okay, so that is our source concentration source term. Okay, and also we are going to give the periodic boundary condition. Okay, so whatever the things coming from the inlet and go to the outlet and must come back again to the inlet. Okay, so that will, in that, without that boundary condition we will not be able to get that loop kind of action in the CFD code. Otherwise it will give a stationary values for everything. So that will, the dynamic behavior will not show if we didn't do the periodic boundary conditions. So we will understand this when you code it up. So please go ahead and try different methods so to clear this point. And is equal to C end minus 1. So I think you are familiar with what is this end means. End means the last node of the matrix. It means end means the last column of the matrix, and end minus 1 is the column before the last one. Okay, so now we are solving the advection-diffusion equation in the entry. Okay, let me pull it a little bit here. Okay, so I'm going to give two for loops. For one is I, where I am from 2 to is equal to in y minus 1. Remember I is rows. Okay, for j is equal to 2 to nx minus 1 and end. Okay, and we're going to give Cn is equal to C now, because the current the value of the concentration at the previous time step is equal to value of the concentration at the current time step, because now the new time step Cn plus 1 is going to be based on Cn. Okay, so Cn is equal to C. So now we know what is the discretized advection part. So it is here. So we are going to write it in the code as it is. Yeah. So whatever this equation, the discretized part of the advection equation, whatever this part, so we are going to write here, and diffusion part we are going to write again. So I'll all this diffusion matrix and advection matrix we are going to initialize. We will write it here now, because we are solving for the channel inlet. Okay, and so advection I comma j, advection value of the matrix of I comma j node, and so we're gonna use I comma j. So we already have u for I comma j, right, into C n I comma j plus 1. Please focus on this, why they are plus 1 and minus 1. I comma j minus 1 by here into dx. Okay, I think it's clear, right? So ui comma j concentration gradient del C by del X, so that will be 2 dx. Okay, why it is 2 dx? Because we are using the central differentiation scheme, so the length between this nodal value and this nodal value is twice of the discretized length in S direction. Okay, so that's why it's 2 dx. And let's try the diffusion part of the advection-diffusion equation for the channel. Diffusion y direction is equal to I comma j is equal to d by dy square into cn comma j minus 2 into cn comma j minus 1. Sorry, should be I comma j. Should be I minus 1 comma j. Plus cn I comma I plus 1 comma j. Okay. Right. Okay. So I'm to save time, I'm not going to write this again. Let's left these two parts because I definitely are understanding this. So I'm going to copy and paste here. So it is turbulent diffusion term. Okay. And so this part is going to be, so now that is the addition of that. Now we are assembling the total advection-diffusion term here. So let's see what is the problem. So now I'll explain how to put the boundary conditions. So let's say boundary conditions. Okay. So let's write the statement first. Diffusion in y direction. I come 1 comma j. So first row j for each and j column d by dy square 2 minus cn I comma j, sorry 1 comma j plus cn 2 comma j. So what we wrote here. So now the diffusion term of the advection-diffusion equation. So we don't in the first row. So basically we don't have one concentration term. The I minus 1 concentration term, we don't have it, right? So what we can do is we approximate the diffusion gradient not from the central differentiation scheme but from the forward differentiation scheme. Okay, so that means for that rather than considering the I minus 1, whatever the node we didn't have, so we're going to get the diffusion gradient or concentration gradient in the first row. That means I is equal to 1, and the second row I is equal to 2. So that means, so the diffusion gradient between this node and this node, and we are taking it as, and we know it is dy. Otherwise if we are taking this one and this one, it's going to be 2 dy square. So but because we are taking only these two, so it's going to be dy square. Okay, cool. Okay, so that is for the boundary condition for the inlet side, the diffusion equation. And I'm going to write, so I'm going to do the same thing for turb diffusion, but I'm not going to write it. I'm going to copy and paste it here. And now again we are using this assembled advection-diffusion equation for that boundary. So now we have all the boundary conditions. We have the boundary conditions for the top part, we have boundary conditions for the bottom part, and also we know that we have the no slip velocity in the bottom, but actually we don't have to mention it in that code. It will automatically generated because we know the velocity is 0 in there, right? So the advection part will be automatically 0 in the u is equal to 0 in the surface interface, okay, in the bottom interface. So advection part will be automatically 0, but we have the diffusion part also, but that will be automatically solved by the code, okay. So I don't know why we forget to initialize turbulent x term. We'll see about that in the later. Okay, so that is basically the end of the discretization of in the inlet channel. Okay, another important thing. So now here you see that we implemented in this part in the core, in this advection-diffusion equation, we implemented the sink term or the adsorption term. Okay, so now Cn as it is mentioned by here, mentioned here. That's it. Okay, as it is here. So Cn Ka dy dt, because A is now how much? It is going to be dy dx into 1. So now we are going to write the diffusion equation for the membrane. So I already wrote the boundary conditions, so please go ahead and write it by yourself. So Cm all rows comma first column is equal to Cm all rows comma the second column. That means the bound non insulator type concentration, that means there's no concentration flux in that surface. So that's going to be because of the, and therefore it is the concentration gradient in that side is equal to 0. So that gives us the two adjacent concentrations near the cells is equal each other. So that is this left side, and this is Cm all rows comma n is equal to Cm all rows comma n minus 1. It is for the right side, okay. And Cm mym and all columns is equal to C1 comma all column means, so that is the bottom boundary condition of the membrane. So that means whatever the concentration at the NYM, and that means in this row and all the columns is identically equal to the concentration at the first column, first row, and the all columns in the inlet channel, okay. And we did the same thing, and the first column row of the membrane it is this one, and all the columns, all these points is equal to the concentration of exit channel. That means CR NY, that means that is the NYth row, okay, of the outlet exit channel and all the columns. So that will be equal to membrane, that means the membrane surface concentration is equal to the adjacent grid point of the inlet and exit channels, okay. That's what it simply means, okay. So let's write the for loops again for the membrane. So 2 to ny minus 1, so 2 to, so I is equal to 2 to ny minus 1, j is equal to nx minus 1, okay. So you know basically ny and nym is both the same because 41. So anyway, I write this as ym. So I'm going to write the so this C again as we did before, Cmn, the the current previous time step is equal to the current time step Cm. So diffusion Ym I comma j is equal to Dm. So the effective diffusivity of the membrane dy square to Cmn I plus 1. So I'm not going to describe it again, so you know the how it is discretized. It's 2 into Cmn comma j plus Cmn I minus 1 comma j. Okay, two brackets, right? So in the same way, I'm going to write, let's see what is the wrong we did here. Seems okay. So I think did we initialize this? Yes, yes. There's a diffusion by m. It should be there. Okay. Right. In the same way, for diffusion x direction, x also we can write the same thing. So, but I'm going to write it. So I'm going to copy and paste it to save time. Okay. And so now we are assembling the total diffusion equation. So please go ahead and type it, but I'm going to copy and paste it. So you're going to add the previous time step plus diffusion in x direction, diffusion in y direction. Okay, and Cm I comma j. Okay, so that's the end of the membrane part. So I'm quickly going to the exit channel. So I'm not going to write this, but I'm going to write, let's type exit channel. So I'm going to give the boundary conditions first. Okay. Okay, so I'll start with the boundary conditions. So in this case, solving these equations for the re-entry channel is a little bit complicated than the inlet and membrane. So, but however, we go step by step. So the first case is the periodic boundary conditions. So that means whatever things coming going from all the rows and end and all, and that will be so that's going to be the periodic boundary condition. And for I is equal to, let me tell you at the last why we are writing like this, minus 1. So we are going from high to low. Okay, so we are going from I is equal to, so initially we went from 2 to ny, right? So now we are going from ny minus 1 to 2. We are going in backwards. I'll tell you why. Nx minus 1 minus 1 to 2. Okay. So we are doing this because now our velocity is in right to left. So previously our velocity is from left to right for the inlet channel in this way, but now exit channel the velocity is in total opposite direction. So if we do the forward differencing, forward counting for for loop by using the for loops, so that's gonna actually mess the results. So because basically the velocity we are implementing from right to left, so velocity has the negative value. So if you count in the positive direction, so that create a mess, and that will not create a that will create some obscure results. So we will not be able to solve it. So to avoid that problem, so we are counting it also from the backward. Okay, so that will not create any problems, and also give the concentration and velocity profiles in that direction. Okay, I think we are all clear about this. Okay, so so what is here? So I think we just lost some end here. Yes. Okay, what is this? Y4. For y is equal to ny minus 1. Okay. So again, we are doing the same thing. CRN, that is previous time step, is equal to CM. Same as, you know, advection part is same, diffusion part is same, diffusion part is same. So I'm going to copy and paste. It is same as the inlet channel. Okay, so I'm going to copy and paste these three terms. And again I'm writing the assembled advection diffusion equation. And now again the boundary conditions comes. So this part is same as for the top row, the first row, and all the columns, and first row, the all columns. So it is same as for the inlet channel. I'm going to copy and paste it again. Okay. And again I'm assembling the advection-diffusion equation for that level, that first row and all the columns. Okay. Again now again we are assembling the advection-diffusion equation for the interfaces. This is I'm writing for the bottom. So this is the top row of the exit channel. That means here in this row, and second one is for the next row, the bottom row. Okay. So I wrote the diffusion, and okay, let's copy and paste it here. Okay, now focus that. So in this case, so you see that we introduce the KD term here, CRN ny minus. So how we actually, so this term is introduced here. Okay, desorption term. So SD means KD. I think it's clear. So because and now again we are giving a different way of method, because we don't have the specific concentration of the inlet, okay, for the exit channel. Okay, so what is the inlet of the exit channel? It is here. Okay, it is this surface, right? So you know that in the inlet of the inlet channel, so we gave a concentration of 7.48, right? So we don't know the concentration here. So what we're going to do is we're going to solve the diffusion equation freely for that surface. So it will automatically generate its own concentration when we run when the time is evolving. Okay, so I'm going to copy and paste. Okay, so please focus on that. Okay, so because we don't so in diffusion terms we don't have some of the concentration values like I+1 values, you know, because it's the last row, sorry, last column of the right side. So we're going to reduce the diffusion equation, the concentration gradients for the, that means if you are focusing on the x column. Okay, so we are going to write the concentration gradient between nx and nx minus 1 columns. Okay, so that's what it is written here. I think please type by yourself so you will understand it once it is done here. Okay, so I think we are done with that. So let me correct this. What is 7? This 4. Okay. So now we have wrote all the 3 parts of the governing equations in discretized form for inlet, membrane, exit. So I did some mistake here. For I should be for is j is equal to, so I missed j first, so I corrected it. So now the for loop is okay. Another thing is I already introduced 2 matrices, the diffusion XR and the diffusion X to avoid confusion. So I just put it here, and one of the diffusion X here and diffusion XR when I'm initializing matrices in the first part. So that's the only change I did. So now we already done with the discretized part. Now it is plotting. So let's go to plot. So what I'm going to do is I'm actually not going to write again. So anyway, I'm going to display time here. What are the elapsed time? So time will be displayed, how much time we are going to simulate, and so I'm going to copy and paste this part. So this is basic plotting process of MATLAB. I think you're already familiar with. Please go ahead in the MATLAB resources to know how to do plotting. So what is this at points curve 1 t comma CRT, that is plotting of the so the at points are necessary to plot the live plot to plot it in the live basis. So please know how this actually the MATLAB syntax. Okay, so please go to MATLAB resources and to know how this syntax is actually created. And again same way. So these are subplots. Subplot 3, 2 actually, subplot 1. Okay, so this subplot will plot the inlet concentration, and this will plot the membrane concentration, and this subplot will plot the outlet concentration. Okay, and these are axis labeling, shading, like see axis arranging axes, so these are all I'm not going to give in detail, but there are a lot of resources available in MATLAB libraries to study those. And shading, these are actually optional things, but I added here, and again Y label and X label, title and everything. Okay, so it is time to run the code. Okay, now let's run the code. So I'm going to hit run button. Okay, so it is now pollutant is introduced, and it is going through the inlet channel. Okay, you see here in a small way that it is actually kind of entraining to the membrane, and it is trying to diffuse in the membrane. And already, even though our color scheme is not that much, we have the resolution as much, but see, there almost some part is actually diffused to the exit channel. So you see that there's a boundary layer is actually generating in the exit channel. So let's run this for a few seconds, and now you see that that concentration is some kind of concentration gradient is generated in the membrane also, and it is proportional to the whatever the inlet concentration we have of the species. So don't mind about the top boundary layer in the exit channel, because we have given that boundary, because basically we developed this model for some kind of a sandwich structure of membranes. There are adjacent channels for each membrane. So this boundary layer will represent in the top, it will represent the diffusing of the diffused species from the top part of the membrane. Okay, So there is another membrane located above that. So that's what it's representing, but at the moment you don't have to focus on that. So you see we got the two boundary layers developed, and we see it's diffusing through the membrane, and it is entering to the exit channel and again flowing back. So please go ahead and run it for a sufficient time, maybe for 10 minutes. So you'll see, you will get the ideal or the steady state condition, and so steady state condition should be look like this, should be like this. So that's going to be all. So I believe this video is going to help you in developing discretized codes for advection and diffusion. So I hope to see you in the next video.